an IITG person promises only what he can deliver, and an IITG person delivers what he promises.
Today we will be discussing about semiconductor materials. Semiconductor materials are the backbone of electronic devices and circuits. So what is a semiconductor material? Probably all of you know about conductors and insulators. Now conductor is a material which when you apply a voltage surge, it creates a generous flow of charge. Like for example, copper. Copper is a metal and metals are conductors. Now insulator is a material that offers a very low level of conductivity when a voltage is applied. For example, mica. Now semiconductor material is in between this conductor and insulator. So it is a material that has conductivity level somewhere between the extremes of an insulator and a conductor. For example, germanium and silicon are these two materials which are semiconductors showing similar property. As you know, the resistivity of a material is inverse of conductivity. So if we compare the resistance levels of conductors, insulators and semiconductors, we see that the conductor has resistivity value which is the least among the three. That is typically a copper, which is a conductor, has a conductivity maximum, so its resistivity value is around 10 to the power minus 6 ohm centimeter, whereas an insulator has a resistivity of 10 to the power 12 ohm centimeter, which is much more than conductor. But in semiconductor, like germanium and silicon, have resistivity values in between these two. For example, if we consider a germanium semiconductor, it has resistivity value of 50 ohm centimeter, and silicon has resistivity value of 50 into 10 to the power 3 ohm centimeter. So you can see that semiconductor has resistivity in between conductor and insulator. Now if we consider these three, insulator, conductor and semiconductor, and see their energy band diagrams, then we find that the energy gap between the valence band and a conduction band in an insulator is very high. It is around 6 electron volt as is seen here. So this energy gap means it is a forbidden band, and the electrons will have to acquire this much of energy to become conducting and enter a conduction band. But semiconductor does not have such a high forbidden energy gap, which is around 1 electron volt as is seen here. So electrons can acquire that much of energy, which is 1 electron volt only, to jump from valence band to the conduction band in order to become conducting. And metals like copper, which are conductors, they have overlapping conduction band and valence band, and they have 0 electron volt. That is why they are so much conducting, because electrons can very easily shift between valence band and conduction band and take part in conduction. So semiconductor is a material that has conductivity level between the extremes of insulator and the conductor that we have seen. And why this is so? That is because the semiconductor like germanium and silicon, they have some unique qualities which are due to their position in the periodic table and their atomic structure. These are group 4 elements. So the atoms of these materials like germanium and silicon, they have a very different and definite pattern that is periodic in nature. That is, it continuously repeats itself, and one complete pattern is called a crystal, and the periodic arrangement of the atoms is a lattice. Now both germanium and silicon have 4 electrons in the outermost orbit, which are called valence electrons. Now in order to complete the structure of inert gas, they will always try to complete the 8 electrons in the outermost orbit. So in the pure germanium or silicon crystal, these 4 valence electrons will be bonded to 4 neighboring atoms, as is shown in this diagram. So here, as you can see, if I consider a germanium atom, so it has 1, 2, 3, 4 electrons in the outermost orbit, which are called valence electrons. Similarly, silicon will also have 4 electrons in their outermost orbit. These are because they are group 4 materials. Now they will be trying to complete the 8 electron structure in the, so that is why they will be sharing electrons with their neighboring atoms, as is seen here. If we consider a silicon atom, these 4 electrons in the outermost orbit, they are sharing electrons among themselves, so that the total number becomes 4 and 4, 8. So these atoms which are nearby, they are sharing these covalent bonds. So these covalent bonds are formed between neighboring atoms of silicon, and thereby they complete the structure of the inert gas having 8 electrons in the outermost orbit, so that they become stable. So these semiconductors, which are in the purest form, are known as intrinsic semiconductors. So in these intrinsic semiconductors, the free electrons are due to only natural causes like thermal energy or light energy, which impart extra energy to the electrons to become free, and thereby they get additional kinetic energy from these natural causes, and they break these covalent bonds. These covalent bonds, they will be breaking in order to become free. One electron will become free when it absorbs kinetic energy from either the surrounding or any light is falling on them. Now an increase in temperature, which is naturally the reason for more conductivity in semiconductors. So this increase in temperature of a semiconductor results in increase in the number of free electrons in the material, so they become more and more conductive. So even though they may be not so conducting at a certain temperature, but if we increase the temperature, they will be absorbing more kinetic energy and will become more conducting. So the semiconductors like germanium and silicon, they have negative temperature coefficient, as the resistance will be decreasing with increasing temperature. This is a peculiar phenomenon that is seen in semiconductors, which is just opposite to your conductors like metal. Now we have been talking about the intrinsic semiconductors. Those are the purest form of semiconductors without any impurity in them. But there is another type of semiconductor, which is extrinsic semiconductor, it is called. Now this extrinsic semiconductor has the characteristic such that their property can be significantly altered by addition of certain impurity atoms into the pure semiconductor material. So, but what type of impurities will be added to the purest semiconductor to make an extrinsic semiconductor are defined. Like we can add pentavalent impurity materials like antimony, arsenic and phosphorus, which are group 5 elements and have 5 electrons in the outermost orbit. Or we can add trivalent materials like boron, gallium and indium, which are group 3 materials and have 3 electrons in their outermost orbit. And the standard norm of adding is that they are added 1 part in 10 millions. That is, in 10 million of atoms of intrinsic semiconductor, you add an impurity atom, 1 impurity atom. Now, how this addition of these impurities totally change the electrical properties of the intrinsic semiconductor material, that we will be discussing. So, when certain impurity atoms like antimony or boron are added to a pure semiconductor material, we get an extrinsic semiconductor. And this process of adding certain impurity atoms like antimony or boron into pure semiconductor like silicon is called a doping process. As a result of this doping, we get extrinsic semiconductor, either N-type or P-type. That is, you can get N-type extrinsic semiconductor if you add pentavalent impurity material like antimony, phosphorus into a pure semiconductor like germanium or silicon. Or you can have P-type extrinsic semiconductor when you add trivalent impurity material like boron or indium into a pure germanium or silicon semiconductor. But what happens when you add an impurity atom to a pure semiconductor? So let us take, for example, an N-type semiconductor, how it is formed. Now, as N-type semiconductor means we have to add pentavalent impurity material. So let us take the example of adding antimony, which is a pentavalent impurity material, which is a group 5 material having 5 electrons in the outermost orbit, to a silicon semiconductor. Now, this silicon atom has 4 electrons in the outermost orbit. So these are silicon outermost orbit electrons. And now, as we have added 1 antimony atom which has 5 electrons in the outermost orbit, so it will be sharing these electrons with the silicon atoms, like these covalent bonds will be completed. 4 and 4, 8 electrons are there, so these covalent bonds will be completed. But then 1 electron is in excess, that is, it is extra. So this 5th electron is donated by this antimony atom. Now, which is this 5th electron is free. It can take part in conduction easily. That is why it is donating as 1 electron. So it is excess of 1 electron which is negatively charged. So this is called N-type semiconductor. What happens when we add P-type semiconductor? So we have seen how N-type semiconductor is formed by adding pentavalent impurity material to intrinsic semiconductor like germanium or silicon. Now let us see how P-type semiconductor is formed from pure semiconductor like germanium or silicon by adding trivalent impurity material like boron or indium. Now let us add boron impurity, which is a group 3 material having 3 electrons in the outermost orbit, to a silicon semiconductor. Now this boron has 3 electrons in the outermost orbit, so it will be completing its covalent bond with a neighboring silicon atom having shared these 2 electrons as is seen here. So these two electrons will form a covalent bond. So in this process 3 covalent bonds are now completed. But what about the other covalent bond? This covalent bond is now devoid, or it is short of 1 electron to complete its covalent bond. So this shortage of 1 electron means it is having a less negative charge. So this less negative charge or a positive charge is there in this covalent bond. So this is called a hole. Hole means it is basically devoid of one electron. So there is a hole formed here in this covalent bond, and this hole is a positively charged particle. So this p-type semiconductor basically is formed in this way, which will be having holes as charge carriers. So now if we consider again the n-type material, we have seen that in n-type material, which is an extrinsic semiconductor, it has donated one electron. So as it has donated one electron, the atom of this extrinsic semiconductor is now having one positive charge, which is called an ion. So one atom of this extrinsic semiconductor, when it donated one electron, it has become ion having one positive charge, which is shown here. So the donor ions are having one positive charge, and there will be electrons which are in abundance in the n-type material. These are called majority carriers. So in an n-type material, the majority carriers are electrons, but there will also be in less numbers minority carriers, which are holes. These holes will be from this intrinsic material that is coming. So if n-type material is considered, altogether we will be seeing majority carriers as electrons, minority carriers as holes, and immobile ions which are positively charged are donor ions. They are there. This is the structure of an n-type material. Similarly, if we consider a p-type material, since p-type material has acceptor ions which are formed because if we consider the p-type material, then we have seen that there is a hole, and as it is devoid of an electron, it will be always trying to get an electron from the neighborhood atoms. So the electron from the neighborhood atom will come and fill up this hole, and as a result this boron atom will be now, it will be negatively charged. So it is accepting one electron, so it will be negatively charged. So that means in a p-type material, the atom of the impurity will be an acceptor ion having a negative charge, and there will be holes which are positively charged as majority carriers, and also a very less in numbers, although there will be presence of minority carriers which are electrons, which are coming from the intrinsic semiconductor. So this is p-type material where all these carriers and ions you see here. So now we can summarize that in n-type semiconductor, the majority carriers are electrons and minority carriers are holes, and in p-type semiconductor, majority carriers are holes but minority carriers are electrons. So these are the charge carriers available in n-type and p-type semiconductors. Now if we consider how the current flows in a semiconductor, you know, so far you have been getting that current flow is due to the movement of electrons, and conventional current is always against the direction of movement of electrons. Suppose if electron moves in this way, then conventional current direction will be in opposite way. This is electron movement direction, and this is conventional current direction. But now we have seen that another type of charge carrier is also there in the semiconductor, which are holes, which are positively charged. So the current flow will be now due to these two types of carriers. One is electron and other is hole, and both are opposite in charge. That is, electron is negatively charged and hole is positively charged. So now suppose we are having a semiconductor as is shown here, and we have the silicon atom, and this is an impurity atom which is boron. Now it is creating a hole as is seen here. So in order to fill up this hole, electron from a neighboring atom will come. So this movement of electron will be in this direction. When this electron comes and fills up this hole, then this place will be now devoid of electron and it will be now a hole. So now hole movement will be from this position to this position. It is just opposite to the electron movement. Electron movement is in solid direction of this arrow and hole movement is in this dotted direction of this arrow. So if we consider the current direction, conventional current direction, which is opposite to the direction of movement of electrons, then the current direction will be in the same direction because of both these components. If I consider conventional current direction, it will be in this because this electron movement is in this direction and hole movement is in opposite direction, but the total direction of current which will be flowing, it is opposite to the electron movement, so it will be in the opposition to this movement of electron, but that is the same direction of the hole movement. Now we will be discussing a very fundamental and very important law which gives the relationship between electron and hole concentration, and that is known as mass action law. Now what is that law? First of all, we must know it states that under thermal equilibrium, the product of the free negative and positive concentrations is a constant independent of the amount of donor and acceptor impurity doping. That is, mathematically if we write Np is equal to Ni square, where N is the concentration of free electrons in thermal equilibrium, P is the concentration of holes in thermal equilibrium, and Ni is the intrinsic carrier concentration. This is a very fundamental law in electronics, which is mass action law. Now let us consider about the charge densities in a semiconductor. So as we will be considering charge density later, before that, what is the law of electrical neutrality that is satisfied in the semiconductor also, that we must know. Now let us consider a semiconductor material and consider a situation where it is doped by both n-type and p-type semiconductor, p-type materials, and consider that Nd be the concentration of donor atoms. These donor atoms are all practically all ionized, and already we have seen that these will be positively charged donor atoms. So we have Nd positive charges per cubic meter which are contributed by these donor ions, and let P be the whole concentration in the semiconductor. So the total positive charge density in the semiconductor is Nd plus P. That is total charge, positive charges per charge densities in the semiconductor, which is contributed by donor atoms as well as holes. Similarly, if we consider that Na is the concentration of acceptor ions, then these contribute Na negative charges per cubic meter, and let small n be the electron concentration in the semiconductor. So the total negative charge density in the semiconductor will be now Na plus N. And since this semiconductor is electrically neutral, so we have this law to be satisfied, that Nd plus P is equal to Na plus N. So let us number this equation as 2. That means this electrical neutrality must be satisfied in the semiconductor given by this equation. Now if we consider a solely n-type material, because we can either dope by n-type or by p-type impurity. So in an n-type material doping, Na will be obviously 0. And then the equation 2 will be now boiling down to Nd plus P is equal to N, since Na is equal to 0, or Nd is equal to N minus P. Now as it is an n-type material, the and concentration of electrons is much more than concentration of holes. So n minus p we can roughly say that equal to n. Then we get that from this equation we will be getting that electron concentration is almost equal to the concentration of the donor atoms, Nd. And so if we use a subscript small n, the electron concentration in an n-type material, Nn is equal to capital N subscript capital D. So we can now get, from this equation we can get now hole concentration for this n-type material, which is given by Pn is equal to Ni square by Nd. Here we are using equation number 1, mass action law. Similarly, if we consider a p-type material, then in p-type material the donor concentration is 0 since it is a p-type material. So the equation 2 will be now reducing to p is equal to Na plus small n, or Na is equal to p minus n. And since it is a p-type material where the hole concentration is much more than electron concentration, so p minus n can be approximately written to be equal to p. So we get finally in the equation 2 we get p is equal to almost equal to Na. So in a p-type material, hole concentration is approximately equal to the density of acceptor atoms. So if we use a subscript small p, p subscript p is equal to almost equal to Na. And similarly from equation 1, mass action law if we use, we can find out the concentration of electron in a p-type material, which is equal to Ni square by Na. Just here I am substituting in this equation Np is equal to Ni square, I am substituting this p with Na. Then I get this n equal to Ni square by Na. So we have got this fundamental difference between a metal and a semiconductor in the way that metal is unipolar, since current conduction is taking place only by electrons, which is having only one sign, that is negative sign. But in semiconductor there are two charge carriers having negative as well as positive charges, which are known as electrons and holes. So semiconductor is a bipolar material. There are two types of charge carriers, positive as well as negative, which are positively charged are holes and negatively charged are electrons. So whenever you apply an electric field, capital E say, then your holes and electrons will be moving in opposite directions since they are of opposite sign, but the current due to both of these components will be in one direction. So the current density, if we want to find out after the application of an electrical field E, that is given by this expression. The current density J is equal to N times mu N plus P times mu P into Q into E, which can be known as sigma into E. Now, what are those terms? N is magnitude of free electron concentration, mu N is mobility of the electrons, P is magnitude of the hole concentration, and mu P is the mobility of holes, Q is the charge of an electron, and sigma is known as conductivity, which is given by this expression N mu N plus P mu P into Q. Now for intrinsic semiconductor, as N is equal to P, which is equal to Ni, that is intrinsic concentration. So we get for intrinsic semiconductor, if we want to find out the current density, you will have to simply substitute Ni for N and P both. Now let us take one example and see how you can find out the current density. The example is to consider an intrinsic silicon bar of cross section 5 centimeter square and length 0.5 centimeter at room temperature 300 degree Kelvin. Now an average field of 20 volt per centimeter is applied across the ends of the silicon bar. So it is the silicon bar having a cross section of 5 centimeter square, and you are applying an electric average field of 20 volt per cm. So now you are to calculate electron and hole component of current density. total current in the bar, and resistivity of the bar. These three you have to find out. Now, you are given that the mobility of electrons is 1400 centimeter square per volt into second, and hole mobility is 450 centimeter square by volt second, and intrinsic carrier concentration of silicon at room temperature 300 degree Kelvin is generally taken as room temperature. You know Kelvin is T, small t degree centigrade plus 273 degree, that gives you the Kelvin temperature. So here it is 300 degree Kelvin. So you can find out at what room temperature it is. This example is carried out 300 minus 273. So at 27 degree centigrade room temperature, this is the sample is given. And now at that temperature, the intrinsic carrier concentration of silicon is given as 1.5 into 10 to the power 10 per centimeter cube. Now you have to find out electron and hole component of current density. Now if we are to find out electron and hole component of current density, we must use that equation. This equation is J equal to N mu N QE plus P mu P QE. Now you have to see what are the data given to you. So we know already N is equal to P is equal to Ni in an intrinsic semiconductor. Since this is an intrinsic semiconductor and its value is given in the data as 1.5 into 10 to the power 10 per centimeter cube. Electron mobility and hole mobility are also given. Electron mobility mu n is 1400 centimeter square per volt second, and hole mobility is 450 centimeter square per volt second. But this charge of an electron is not given. It is supposed that you know this, and its value is standard 1.6 into 10 to the power minus 19 coulomb. So it is simple to find out what is this current density J given by this equation. So as you see in this equation, there are two components. One is due to the electrons and the other is due to the holes. So electron component of current density we can find out from this part of this equation. So you just substitute each of these values, N by Ni intrinsic concentration, mu N Q E. E is 20 volt per cm. And each of these are substituted by the given values, then we get this equation. And finally the answer comes 67.2 microampere per cm square, that is the electron component of the current density. This current density is due to the electrons. Similarly, the hole component of current density you can find out, that is P mu P Q E. Here also you substitute all these given values and you find 21.6 microampere per cm square. That comes to be the hole component of current density. Another thing you have to find out is the total current. Now this is only current density. So in order to find out the total current, you have to multiply it by the cross sectional area, which is given as 5 cm square. So current density mu A per cm square we have found out. Each of this hole component and electron component that you have to add up. Then you will be getting the total component, total current density. So 67.2 and 21.6, this is the total current density, multiplied by the cross sectional area 5 centimeter square. So finally we get 444 microampere is current flowing in the silicon bar. And finally the resistivity of the silicon bar, as you know, it is inverse of conductivity. 1 by conductivity gives you the resistivity. Now conductivity sigma is again given by N mu N plus P mu P into Q. So 1 by this whole term. So that will give you the resistivity, and substituting each of these values we get finally the resistivity of the silicon bar is 22.52 into 10 to the power 4 ohm centimeter. So this, in this example we have used only one equation, that is the current density equation. The rest of the things are found out just from that. So in this class of today we have learnt about intrinsic semiconductor material as well as extrinsic semiconductor material and their characteristics or properties we have studied, and this semiconductor is the main component in all electronic applications and devices, which is made of intrinsic semiconductor is silicon or germanium, and when it is doped with impurity atoms like pentavalent or trivalent materials, then we get n-type as well as p-type semiconductor, extrinsic semiconductors. So these will be used in all electronic devices. So in today's class, we have learnt about intrinsic as well as extrinsic semiconductors, how extrinsic semiconductors are formed from intrinsic semiconductors by doping them with p-type or n-type p-type or n-type materials, and we have also seen the characteristics or properties of these extrinsic semiconductors. So now this semiconductor is used as a backbone in all semiconductor devices and circuits. Now let us try one example. Consider an intrinsic silicon bar of cross section 5 cm square and length 0.5 cm at room temperature 300 degree Kelvin. An average field of 20 volt per centimeter is applied across the ends of the silicon bar. Now part A, calculate number 1, electron and hole component of current density, number 2, total current in the bar, and number 3, resistivity of the bar. Now part B of the problem is, if now donor impurity to the extent of 1 part in 10 to the power 8 atoms of silicon is added, find the density of minority carriers and the resistivity. Now the given data to you are, electron mobility is given as 1400 centimeter square per volt second, hole mobility is 450 centimeter square per volt second, intrinsic carrier concentration of silicon at room temperature 300 degree Kelvin is given as 1.5 into 10 to the power 10 per centimeter cube, and number of silicon atoms which are doped per meter cube is 4.99 into 10 to the power 28. This last data will be required for the part B of the problem. Let us now first of all do part A of the problem. So it is an intrinsic semiconductor is given. So the hole concentration and electron concentration is same, which is the intrinsic concentration, and it is given as 1.5 into 10 to the power 10 per centimeter cube. Electron mobility is given as 1400 centimeter square per volt second. Hole mobility is given as 450 centimeter square per volt second. And charge of an electron, that is of course not given, but you should know this value, which is 1.6 into 10 to the power minus 19 coulomb. So with this data, we will be now finding out the current density first. As you know, the current density J is given by N mu N Q into E plus P mu P Q into E, where E is the applied electric field and all the other data are given to you. So now this current density has two components, one due to the electron and the other due to the hole. Now electron component of current density, when you find out, this electron component of current density will be the first part. This part will be the electron component of current density, and that is equal to, you just put down the values, and you know that electron concentration is nothing but intrinsic concentration. So it will be Ni mu N Q into E. So now substitute the values which are known to you. Each one we will be substituting now. Ni is 1.5 into 10 to the power 10 per cm cube, and electron mobility is 1400 centimeter square per volt second. Q, charge of an electron, is 1.6 into 10 to the power minus 19 coulomb, and the applied electrical field is 20 volt per cm. All these are in cm, that you must be careful, because all centimeter is the unit all in all the data. So now if you calculate this value, then we are getting 67.2 microampere per centimeter square. So part 1 of the problem A is now 67.2 microampere per centimeter square. Now part 2, whole component of current density, that has to be found out, and that is the second part of the equation J, which is P mu P Q into E, and that can be replaced by Ni mu P Q E, because Ni is the intrinsic concentration, that is equal to hole concentration as well as electron concentration in intrinsic semiconductor. So now substituting each of these values, Ni is 1.5 into 10 to the power 10, then mu P is 450, Q is 1.6 into 10 to the power minus 19, and E is 20. So we now calculate this, and the result is 21.6 microampere per cm square. So that is the whole component of current density. Now third part of the problem says that you have to find out the total current in the silicon bar. So in order to find out the total current, you have to multiply the current density J by the cross sectional area. So the total current in the bar is equal to the current density into the cross sectional area of the bar. So that will be current density is the total current density due to the holes as well as electrons. So we have to sum up these two, 67.2 plus 21.6 microampere per cm square, and multiply it by the 5 cm square cross sectional area, and that gives the result as 444 microampere is the total current. And the next part of the problem is resistivity. Sorry, this is part 3. This was part 2. Part 3 is resistivity of the silicon bar. So as you know, resistivity is 1 upon conductivity, and conductivity sigma is n mu n plus p mu p into q. So if you substitute all these values, which we already have with us, because n and p is nothing but Ni, so I can write it as Ni can be taken out, Ni into q, then mu n plus mu p, which will be giving you the resistivity, and that is equal to 22.52 into 10 to the power 4 ohm centimeter. Now we come to the part B of the problem, in which you have to find the resistivity of the doped semiconductor as well as its minority carrier concentration. So if you look into the problem, it is doped, and the doping impurity is, it is an N type of doping material. Donor impurity is 1 part in 10 to the power 8 atoms of silicon. So in the part B of the problem, you are doping with silicon, doping silicon with donor atom. So the concentration of donor atoms, Nd, which will have to be found out, and we have been told that the doping is 1 in 10 to the power 8 atoms of silicon. But we also know, and it is given in the problem, that number of silicon atoms per meter cube is 4.99 into 10 to the power 28 is the number of silicon atoms per meter cube. Now, we are doping it 1 in 10 to the power 8 silicon atoms. So, what will be the donor concentration? So, donor concentration will be 4.99 into 10 to the power 28 divided by 10 to the power 8. So, this value is 4.99 into 10 to the power 20 atoms per meter cube. Now, you have to be careful. This is given in per meter cube. That is, concentration is given in per meter cube. But other data in the part A of the problem were in per centimeter cube. So, be careful about this, and you have to multiply or divide wherever necessary to have a conformity in the units. So, now what will be this majority carrier density Nn, which is almost equal to Nd in n-type semiconductor. So, we can write it as 4.99 into 10 to the power 20 atoms per meter cube. So, now minority carrier density, which is asked. So, obviously minority carrier here will be holes. So, minority carrier density, that is hole density, we have to find out, and we know from our previous discussion that Pn is the minority carrier density in n type of material is Ni square divided by capital N capital D. So, now when you replace, you have to see, because Ni in our example is given, if you look into the problem, it is given as 1.5 into 10 to the power 10 per cm cube. But here you see that Nd is per meter cube. So, we have to bring conformity by multiplying or dividing accordingly. So, now I will be finding out this whole carrier density, that is minority carrier density. So, that is 1.5 into 10 to the power 10 per cm cube is given, divided by 4.99 into 10 to the power 20. But in this way, it will be wrong if I do like this, because this is in per meter cube. So, I have to bring this numerator to the same unit as in the denominator. So, I will have to bring this centimeter cube to meter cube. So, 10 to the power minus 2, we will have to multiply it to get it into meter. So, it will be 1.5 into 10 to the power 10 divided by 10 to the power minus 2 into 3, that becomes 10 to the power minus 6. Then it will be coming per meter cube. Of course, there is a square, and in the denominator it is 4.99 into 10 to the power 20. So, all are in now per meter cube, here also in the denominator also. So, if I calculate this, then I get this value as 4.51 into 10 to the power 11 holes per meter cube, because I have brought it into meter cube. So, the whole concentration now is 4.51 into 10 to the power 11 holes per meter cube. Now, next part I have to find out resistivity. So, resistivity is 1 upon conductivity. So, you just replace these values. Sigma is equal to Nn mu n plus Pn mu P into Q. So, it will be equal to, here Nn electron concentration is 4.99 into 10 to the power 20 into mobility of electron is 1400, but it was 1400, electron mobility was 1400 cm square per volt second. So, I will be converting everything to meter unit. So, I will have to multiply 10 to the power minus 4 with 1400 plus the whole concentration I have found out 4.51 into 10 to the power 11 this many holes per meter cube into the mobility of holes is 450. Again I will be multiplying by 10 to the power minus 4 to bring it into beta square unit. The whole thing I will have to multiply by Q, which is 1.6 into 10 to the power minus 19. And this calculation gives me the whole numerator will be 11.1777. So I will be getting 0.08946 ohm meter. Now I can convert it to ohm centimeter just to see the difference, how the resistivity changes when you are doping an intrinsic semiconductor. So if I convert it to centimeter multiplying by 10 to the power 2, then I get it is 8.946 ohm centimeter. Now just you compare what was the resistivity when you had only intrinsic semiconductor, and that intrinsic semiconductor had a resistivity we have done in the part 1 of the part A of the problem, and that was 22.52 into 10 to the power 4 ohm centimeter, that was of the intrinsic material. Now when we doped it with a material, then that doping material is donor, so that doping has brought down this resistivity to 8.946 ohm centimeter. If I find out how much ratio it has brought it down, dividing this by 8.946 ohm centimeter, then I find that 25,173.26 times the resistivity of the material after doping, it has been brought down. So this effect of doping an intrinsic semiconductor by an n-type or a doping agent is very important, because it has brought down the resistivity, means it has increased or enhanced the conductivity so much. So this example illustrated the effect of doping an intrinsic semiconductor by an external n-type impurity atom that we have learned today.